Okay, we're now, should be live. Let me check the video on the web. Yeah, we're now live.
Okay, so welcome everyone. Today's TCS Plus by Avishay Tal. Um, uh, Before we start, let me thank Thomas Vidic, who's helping me here with the operation and also behind the scene. Other organizers, Gautam Kamat, Clement Canon, Ilya Rosenstein, and Anindya De. So before we continue, let's quickly go around the table. We have see some new faces this week. So Thomas.
Yeah, so welcome to the groups who are joining us. So first we have a group led by Clement Canon from Colombia. Welcome, guys. Then we have Ehsan from USC. Welcome, Ehsan. Then I see a group led by Janish from Caltech. Welcome, guys. Then there's a group led by Shravas from NYU, is it? Yeah, NYU. Then Sina is joining us from University of Michigan. Welcome. And Sorashai is joining us from Michigan State. Welcome. And then there's our European friends, Srini Vasan from and company from CWI. Welcome. Okay, I think I'm going around the table.
Great, thank you, Thomas. Just if you, great. Let me remind you that before we start, the next talk is in 2 weeks. We have Mohsen Ghaffari from ETH Zurich. And today's speaker is Avishay Tal. We're very happy to have Avishay. Avishay graduated in 2015 from the Weizmann Institute. His supervisor was Rani Raz. Currently postdoc at the Institute for Advanced Study. He's done lots of great work on computational complexity, specifically circuit complexity, matrix rigidity, and other questions. And today tell us about another exciting recent work of his. So Avishay, welcome.
Thank you very much. So thank you again for the invitation to speak here. I feel really honored to speak in this forum, and thank you all for joining me today. So I will talk about a recent result called Computing Requires Larger Formulas Than Approximating. This work will be presented in the following stock. So the model that I'm discussing today is De Morgan formulas. This is a model of computation, and we will talk about Boolean functions. We will identify the Boolean domain by plus and minus 1. Minus 1 represents true, and 1 represents false. And a Boolean function simply takes n such bits and output 1 bit. In order to compute a Boolean function, we may use De Morgan formulas. These are just binary trees where each internal node is marked with a gate, either or AND, and each leaf is marked with a variable or its negation. So for example, this formula computes the function x1 and x2, or x1 naught and x3. And you can see that you can write any formula as a one-line mathematical expression as done here. And this is why we call it a formula, actually. So two important complexity measures for Boolean functions that we will use is the formula size and the formula depth. The formula size, or L of f, is the minimal size of a formula computing f. So we may have several formulas computing the same Boolean function, and we take the minimal such one. And by size, I mean the number of leaves, which is up to a constant of 2. It's the same as the number of nodes, because this is a binary tree. Okay, so in this case, the size is 4. We have 4 leaves, and actually this is the best formula to describe this function. The second parameter, the depth, simply measures the longest path between the inputs and the output. The length of this longest path is called the depth. In this case, it's 2. And again, we'll have several formulas computing the same function, so we simply take the minimal one. And depth really captures something very important, which is the parallel time. Think of all these nodes as working in parallel. The time that it will take the values to propagate from the inputs to the output correspond to the depth. Okay, so if in 2 time steps, we will have the value ready at the root here in this formula, for example. This is really motivated by understanding parallel computation, as we'll see in the next slide. Result from the 70s showed that really we have a very intimate relation between the depth and the size. So the optimal depth for a given function is up to a constant log the optimal size that we have. So really, if you want to understand one, it's the same as understanding the other via this connection. So we will focus in this talk on the formula size, but recall that we have this connection that the depth is logarithmic in it. This is not true for any formula, it's just true for that there exists a very shallow formula if there exists a very small formula. Okay, so this is the connection. And the complexity class that we will be interested in is NC1. These are the functions that can be computed by polynomial size formulas or equivalently by logarithmic depth formulas. And these are functions that can be computed very efficiently using parallel computers. They can be computed in logarithmic time. The values will propagate in logarithmic time. And now we reach the motivation for studying formulas. And this comes from the field of parallel computation. We want to understand what is the power of parallel computation. We are reaching an area where a single core almost reaches its limits. And in order to make computers faster, we are introducing more and more cores. The question is, does it help us to solve problems faster? Can we solve any problems 1,000 times faster with 1,000 cores? And it seems intuitive that some problems, some tasks benefit from this parallelism. For example, if you want to dig this very long canal, the more workers you have, the job will be done faster. However, if you want to dig this very narrow hole, this seems inherently sequential. You must dig the first meter before you dig the second meter, and it doesn't seem that more workers will help finish the job quicker. The question is, can we take the intuition of these inherently sequential problems from the real world into the computational world and make it into a proof? And this is really the P versus NC1 question. So in one way to phrase it, can we do anything in P also in logarithmic depth formulas? So can we do anything in P in NC1? Or alternatively, can we do it with polynomial size formulas? This would be amazing. It will mean that you can take any computation that runs in polynomial time and on a parallel computer run it in logarithmic time. But this seems too good to be true because some things are inherently sequential and you could not have this small depth. So really, we think that some problems in P require linear depth or exponential size. And this is a common belief, and we want to be able to prove it. Currently, we are very far from this task, and the best lower bounds that we can prove are only polynomial, are only n cubed. And let's see it in this next slide. So the state-of-the-art formula lower bounds were proved for the function suggested by Andreev in the 80s. So he constructed an explicit function that you can run in polynomial time, actually even linear time. And he proved that the formula complexity of this function is at least n to the 2.5, which at the time was the state of the art. And this lower bound was improved in a sequence of work to roughly n cubed. And this is the best known lower bounds that we have for any problem in P, and even for any problem in NP. So this is, you can ask also this question for NP. Can we have some problem in NP with exponential formula size? And the state of the art that we have here is only n cubed. And this is really something that we need to do before we show that NP does not have polynomial size circuits, because formulas are more restricted models, and we first need to prove that NP does not have polynomial size formulas. And to be a little bit more precise about this lower bound, this is n cubed over log squared n times log n. And this lower bound is nearly tight for this function, because a straightforward computation shows that you can do it actually in time in formula size n cubed over log squared n. So really, you can only opt to improve this log n factor, which is not so big. And if you want to further improve the lower bound, it means that you need to find a new function. And we will see the construction later on in this talk. But now I want to talk about average case computation. So far we described formulas that compute a function correctly on all inputs. But we may relax this notion and ask the formula to compute the function correctly on most of the inputs, 99% or even 51%. Does this task become easier? So average case lower bounds shows that for some tasks, it's even hard to compute the function correctly on 51% of the inputs. And this is really motivated by de-randomization, cryptography, and much more. And you can see that in cryptography, for example, you don't want the function to be just hard on the worst case input. You want it to be hard on the typical input. So I will use the following definition, the following notation. I will say that the function is s, half plus epsilon hard if any formula of size at most s agrees with this function on at most half plus epsilon of the inputs. In other words, if you want to get agreement more than half plus epsilon, then you need a formula of size bigger than s. Okay, so this will show that some tasks, even for getting 51%, you need a large size. And I want to mention a few results from the literature that show this kind of hardness results. So the first result by Raoul Santanam, he showed that linear size formulas have agreement at most half plus 2 to the minus omega n with parity. This result is tight. And I want to mention that notice that we always have half plus something. Getting half is trivial because we can just output a constant. And one of the constant will have agreement half with any function. So really, we're interested in how much can we get above this trivial bound. And here, even getting exponentially, we cannot get even more than exponentially small in n advantage. This result was generalized by Impagliazzo and Cabanets, and they showed that not only for linear size formulas, but for size between n and n squared, for size n squared over k, the agreement is at most half plus 2 to the minus k. And again, this is a tight result. It's tight up to this factor of little of 1 that may be improved. And the last result that I want to mention is our result with Ilan Komargodski and Ran Raz. We constructed for any parameter k between 1 and square root n, we constructed the function for which any formula of size n cubed over k squared has agreement at most half plus 2 to the minus k. So I want to note a few things about this result. First, the parameters are better than what we got for parity, because we get the same agreement, but the size is bigger. The size is n cubed over k squared versus n squared over k. Second thing that I want to mention is that notice that if you pick k to be, k is a free parameter that you can pick as you want. If you pick it to be kind of small, then you would get that the size is almost quadratic. However, you get that the agreement is only on 51% of the input say. So you can see that we nearly match the Andreev lower bounds in the average case. And the third thing is that really, what is this parameter k? This is some trade-off parameter between the size of the formula and the fraction of inputs. If we want the size to be very close to n cubed, we want to pick k to be small. If we want the fraction to be close to half, we want to pick k to be large. And really, we have some trade-off between these two parameters. And one question that we ask in our paper is whether or not this trade-off is necessary. Maybe you can get to the same bounds as you got in the worst case, and with a fraction of inputs, half plus 2 to the minus n to the epsilon. So maybe you don't need to pay in the size when getting exponentially close to half. And we thought that this is a natural question. We didn't have any application in mind at the time. But now I want to tell you about an application for this question. And this brings us to this talk, and we want to understand, can we improve these parameters? And in this talk, we will see that any significant improvement to these parameters will break the n-cube barrier in the worst case. And this is really a barrier that stood from the early 90s, the formula size, in formula size lower bounds. The best lower bounds was n-cube from the beginning of the 90s. And it will be very important and very nice if you could break this barrier. We are not breaking this barrier in this talk, unfortunately, but we are suggesting a way to do it.
I've got a small question about the previous result.
Yes.
Because like for every k less than square root n, you have a function such that you get that trade-off. Is there any chance you could get like invert the quantifiers to get like there exists a function for which you have that trade-off? Because like the for the same function.
So you are saying that you want one function that will work for all k's, for all k.
A little bit like in Pagliazzo-Cabanet's results, but with your parameters, basically. Like one function.
Yeah. So in our paper, we didn't do it. I'm not sure if this can be done, but we haven't thought about it too much. So maybe, so maybe you can combine some of these functions together. I haven't thought about this question too much, so to tell you the truth, but no. So our result works really for any parameter. You get a different function. So the function really depends on the parameter. So it appears as some parameter in the construction of the function. But it will be nice to get one function that is hard for all of them. Okay. Yeah. Thank you for the question. Okay. So I want to return to my point that any significant improvement over the parameters in KRT would break the n-cube barrier. To be a little bit more precise, what is our result? We show that for any function, if you have average case hardness, so if you know that any formula of size S prime agrees with the function on at most half plus 2 to the minus k of the inputs, then automatically you get worst case hardness for a bigger size. You get that if you want to compute this function on all inputs correctly, then you need size S prime times k. And this is really a size amplification hardness reduction. You go from hardness against size S prime to hardness against size S prime times k. You lose something because you start with average case and you go to worst case. But I want to mention that this is highly unique and highly unusual. Most hardness reductions go in the other direction. So you reduce the size and amplify some other parameter. And in this reduction, we manage to amplify the size. I want to mention now why will it break the n-cube barrier. So recall that this is our theorem now written in words. If a function is S prime, comma, half plus 2 to the minus k hard, then the formula size of this function is at least S prime times k. So let's say that you prove that some function is n cube half plus 2 to the minus n to the 0.1 hard. Then by this theorem, you get that in the worst case, you need formula of size n to the 3.1 to compute it. I want to mention that this theorem is tight, and you can see it by the result of Impagliazzo and Cabanet. So they show that parity is n squared over k hard for agreement half plus 2 to the minus k. So if you combine it with our result, you get that the lower bound for parity in the worst case is n to the 2 minus little o of 1. But if you could improve any of these results significantly, this would give you a lower bound which is greater than n squared, which is a contradiction because parity has formulas of size n squared. So really, using these two results, you can see, and the upper bound, you can see that both of these results are tied up to the little o of 1 here and the tilde here. And I think that both of these things can be eliminated. So I think really you can get rid of this tilde and you can get rid of this little o of 1. Okay, and I want to mention that the proof really goes via contrapositive argument. So what we are doing, we are starting with a formula that computes a function exactly on all inputs, and this formula will be of size S. And then we show that there exists a smaller formula of size s over k that agrees with the function of the original formula on at least half plus k to the minus k of the inputs. So really, we show that you can take any formula and find a smaller formula that has some better than half agreement with the original formula. So notice that the agreement is not too good. It's only half plus k to the minus k. But we already said that for the parity function, this is more or less the right answer. So let me state the contrapositive as a claim. We have a formula of size s. We have some parameter k, which is at most square root s, and we will see why it can't be bigger than square root s. Then we have a smaller formula, f prime of size s over k, that have two properties. First, it approximates the original formula. So you have the agreement at least half plus k to the minus k. This will be with respect to the uniform distribution. However, we can do it actually with respect to any distribution, but let's focus today only on the uniform distribution, as all application uses this distribution. The second thing that we get is that f prime is of size s over k. We started with this thing, but moreover, it has more structure than that. You can either write it as a constant function or the end of k smaller formulas of size s over k squared. And so far in the application, I haven't used this structure at all, but it will be interesting if you could take advantage of this structure and exploit it to get better worst-case lower bounds. So this finishes the first part of this talk. In the second part, I want to tell you about the proof. The proof is surprisingly simple. It uses a very beautiful result from quantum computing. In the third part of the proof, I want to tell you about two applications of this hardness reduction. In the first, we will improve on Andreev's lower bound by logarithmic factors. And in the second, we will improve by a factor of n, but this will be for a randomized function. So if you don't have any question, let me start with the proof. Okay. So the proof plan will consist of 4 steps. In the first step, we will take this big formula. Recall that we have a big formula of size s, and we want to approximate it using a smaller formula. So we take this big formula f, and we break it down into k squared subformulas of size s over k squared each. So we simply cut the tree into several subtrees of roughly the same size. In the second step, we will show that you can approximate the big formula using a degree k polynomial over the subformulas. This is kind of a weird creature. This is a composition of a low-degree polynomial with formulas. From this, we will get to something nicer. We will get to an approximation by the parity of k of these subformulas, but this approximation will be weak. And the second approximation is strong, and the third approximation in the bullet 3, it's weak. This seems that we haven't done much so far, because how can we compute the parity of k things? Since we have only n's and or's, to compute the parity of k things, it requires size k squared. So really, in step 3, we approximate f, the original formula, by another formula, which is of size k squared over s over k squared, or order s. So we really didn't change the size by anything, maybe even made it worse. So it seems that we haven't got much in the third step, but really we are really close to the end. And from the third step, it's not too complicated to show that you can also approximate f by the end of k of these subformulas. And this would really give us a formula of size k times s over k squared, which is s over k. And this would be really what we wanted. So this was the proof plan, and now we will see each step in more details. So I start with this decomposition. This is an idea that was brought up in the work of Impagliazzo, Mecca, and Zuckerman. And the exact lemma that I'm using was presented in my work from 2014. So we have a big formula, and we want to break it down into smaller formulas. So more precisely, we want to break it into our top formula of size k squared, with k squared nodes, and to bottom formulas, each with at most s over k squared leaves. So we will have this top formula t, and we will have this bottom formula g1 up to gn. Overall, the size of the entire thing will be order k squared over times s over k squared, which is order of s. So in terms of size, this is roughly the same size. The two formulas really compute the same function, so we didn't change the functionality. We may introduce new nodes, so we may increase the size by a constant factor, but not more than that. And really, if you think how we can do this decomposition, think for starters that f is a complete binary tree. Then we can simply cut this tree in a specific layer, in this layer, and look at all nodes in this layer. And for each node, we have the corresponding subtree, and everything above that will be the top formula, T. Okay, this would work for the complete binary tree. However, the formula may be very skewed. It may be very deep and small. So it may have size, let's say, polynomial in n, but depth linear in n. In this case, we can still do it. We may need to duplicate some nodes, but we will result in a formula of size order of s nonetheless. So you can do it for any formula. You can break it into a top formula of this size and bottom formula of this size.
Small question. So in one of the first slides, you told us that you can always balance a formula. Can't you do that here?
That's correct. So you can balance a formula, but when you balance a formula, you may increase the size by a polynomial factor. And here we don't want to do it. We don't want to pay for polynomial factors because we are working with very delicate analysis. So we really want to amplify the size only by a constant. This is what we get here. So it's true you can balance the formula, but it will give you not optimal parameters.
If you lose a polynomial, that's terrible, right?
Yeah. Maybe it will be even it will be meaningless. Yeah. In this case. Okay, but it's actually the idea is very similar to how you would balance a formula. So you find some subtree, and then you take the subtree, and then you repeat by induction to find additional subtrees in the remaining formula. So it's not too complicated. It's a combinatorial algorithm how to do this decomposition, and it was presented in previous works. So now, after we decompose this thing, let's look what happens under the uniform distribution. So let's say that X, the input for this big formula, is sampled from the uniform distribution over plus minus 1 to the n. This induces some distribution over the inputs to the top formula T. This distribution is not necessarily uniform. Some formulas output may be biased. Some formulas output may be correlated with one another. So really, we don't know that this is the uniform distribution. And actually, I will not use any property of this distribution. So I will just treat it as a general distribution over strings of length n. And now, what is it enough to do? It is enough to show that you can approximate T by an end of k of its inputs with respect to this distribution D. If you can do that, then you can approximate the entire formula with the end of k of the corresponding formulas under the uniform distribution. So you now focus on the top formula T under this arbitrary distribution D. And now let's look at the proof plan revisited. So really, we want to show in the end that you can approximate T by the end of k of its input. So we start by showing that you can approximate it by a polynomial of degree k with respect to this distribution D. Then we show that you can approximate it by a parity of k of its variables. And then we show that you can approximate it by the end of k of its variables.
Okay. There's a small technical question. The bottom of your slides gets clipped here. I don't know if it's only here. Is there a way for you to shrink the window a bit? Like the...
Yes. Is it better?
Yes, thank you. Much better.
Let's go. Can you see everything
No, it's
now?
perfect. Yeah, it's perfect. Thanks.
Okay. Thanks. Okay. So let's start with the first step. And this really, we get to the key ingredient of the proof. And this is a beautiful result from the quantum computing area. So it started with the work of Grover search, and ended in this long line of work. And in this long line of work, it was shown that any formula of size S has a quantum algorithm, making at most square root S queries and getting the value of the formula correct on every input with high probability. So for example, if you take the OR formula, simply the OR of all the input variable x1 up to xn, this is a formula of size n, and Grover search gives you a quantum algorithm that runs in times square root n and gets the value of this formula correct with high probability. If you have a 1, it will answer true with high probability. If you have a 0, all the string is zeros, it will answer 0 with high probability. And this generalizes it to any formula of size S, not just the OR function. And by the result of Beals et al., we know that this implies that there exists a polynomial of degree square root S that approximates the original formula F pointwise with error at most 1/3. So this is really a strong notion of approximation. On each point, the formula and the polynomial differ by at most 1/3. So this is a real valued polynomial. It gets real values, and these values differ by at most 1/3 from the correct values. So now we can forget about the quantum algorithm in the middle and see that we have for any formula a polynomial of degree square root S that approximated pointwise. And this is really a classical result. It talks about formulas and polynomials. However, the proof uses quantum arguments. So really this demonstrates the quantum method. So we prove the classical result using quantum arguments. The same way that the probabilistic method, we prove the existence of combinatorial objects using probabilistic arguments. And it's still open to see whether or not you can give a classical proof for this statement that doesn't go through quantum arguments. And I think this is a nice open problem. And also you can opt to simplify the proof. Okay. So really this is a very strong notion of approximation, and we will use that. So now we are using this key ingredient on the formula T, the top formula that we have. So recall that we broke the original formula into a top formula and bottom formulas. So now we are focusing on the top formula. This top formula was of size k squared. So there exists a polynomial of degree order k that approximate T pointwise with error at most 1/3. Since this works for any point, it means that it works for any distribution. So even though we have an arbitrary distribution of all the inputs, this polynomial approximated well also with respect to this distribution, because it just works for every point separately. To see it more precisely, so for any y, we have that the difference between the values that the formula gets and the polynomial gets is at most 1/3. This means, since the values that the formula gets are plus and minus ones, this means that the sign that the polynomial gets is always correct, and the product between the two is between 2/3 and 4/3. And now we can take expectation and see that when y is sampled according to t, the expectation of this product is at least 2/3. So we have a correlation between t and p under the distribution d. So this really finishes the second step. And now I move to the third step, and I want to now approximate the formula by a small parity. Okay, so recall that we have this formula of size k squared, and we have this polynomial of degree order k that approximates it. We write p as a multilinear polynomial. This is without loss of generality because we are only interested in the values of p on plus minus 1 to the n. So you can always find a multilinear polynomial that agrees with p on plus and minus 1 to the n and has the same degree or even smaller. And this is, we simply write p of y as a sum of monomials times coefficient. So here, each monomial I denote by y to the s. This is simply the product of all yi's where I is in some set s. This is because this is multilinear. And we have some coefficient, p hat s. This is sometimes called the Fourier coefficient, but just think of it as some real numbers that, that you multiply with the monomial. And it's a simple exercise to see that all these coefficients are in absolute value at most 4/3. This is simply because the polynomial gets values between minus 4/3 and plus 4/3. So now, what do we know? We know that p correlates with t. And we know that we can write p as the sum of these monomials. So really, it means that one of these monomials must correlate with t slightly. So let's see it more precisely. We simply substitute p with this sum. So now we have that the expectation of this sum times t of y is at least 2/3. Now we use the fact that all these coefficients are at most 4/3 in absolute value. And we use linearity of expectation. And what did we get? We get that there must exist some set S such that this inner correlation, ys times t of y, is at least 2/3 over the number of terms times 4/3. And now, how many terms did we have? So we are choosing sets of size order k from a domain of size order k squared. So we have k to the order k such monomials. So this is the lower bound that we get. We get that there must exist some monomial that correlates with t with a correlation 1/k to the order k. And what is this monomial? This is really a parity function. So in the plus minus 1 notation, taking product is the same as taking the number of minus 1s modulo 2. So this is really the parity over the set S. Okay, so this finishes the third step. And now we said that it seems that we haven't gone much, but actually it will be pretty simple to go from here to the end. And again, what we will do, we will express this parity function in the end basis. So we go over all possible assignments to the variables in S, all possible assignments Z. We check whether we take the indicator that the corresponding coordinates in Y equals this specific assignment. If this happens, we output Z to the S, which is simply a constant. So really, we can write the parity function as a sum of indicators times plus or minus 1s. And this really shows that one of these indicators must correlate with t, and the correlation should be at least 1/k to the k times the number of terms here, which is 1/2 to the s. So again, we get that the correlation is at least 1/k to the k. So we got that the indicator correlates with t, but what is this indicator? You just look at the coordinates in S, and you check that they get a specific assignment. So this is really like the end function. The only difference is that this is not a plus minus 1 function, this is a 0, 1 function because we took indicators. So it's not too complicated to make it into a plus minus 1 function and maintain the correlation. And you would get, actually there is some small point, so either the constant function correlates with t, but this is something that we covered, or one of the end functions correlates with t under the distribution d. And this brings us back to to the original formula, we get that there exists an end of k of the subformulas that agrees with the original formula f with probability half plus 1 over k to the k over the uniform distribution. So this really concludes the proof of our theorem. Okay, so it would be a good point to stop for question if you have any. Okay. And let me just recall the main theorem, what we showed so far. We showed that if a function is s comma half plus 2 to the minus k hard, then in order to compute it in the worst case, you need size s times k. And this offers us an approach to prove worst case lower bounds. We can prove first average case lower bounds and then convert them into worst case lower bounds. So in all the application, we will go in this direction from average case hardness to worst case hardness. In the proof, we went in the other direction. We started with an exact computation and we arrived at an approximate computation.
Just to check, I understand where that tilt comes from. It comes from the fact that you get correlation 1 over k to the big O of k and not 1 over.
Exactly.
Okay.
So exactly. So if it was 1 over 2 to the k, then the tilt will be eliminated. And I suspect that you can get it, but I'm not sure how to do it. So really, you lose in the
argument.
In the step where you go from p to one of the parities, you lose this factor of k to the k. In going from parity to end, you lose 2 to the k. So there you don't lose too much, but in this step you lose 1 over k to the k. Perhaps you can lose less. I'm not sure exactly. Okay.
Avishay?
Yeah.
It's a small question. So how come, when you have at the end of the day, you will get an end of k subtrees, right?
Yes.
But if the output of each subtree is roughly balanced, you expect the end to be highly unbalanced, right? It's going to be mostly zeros.
Okay. Yes.
How can that guarantee correlation that's half plus anywhere near?
So let's say that I equal 1 with probability epsilon, but whenever I'm equal 1, I'm correct. Then this gives me correlation half plus epsilon. Because on the ones I'm correct, but on the zeros I'm correct with probability roughly half.
Okay, that's what you meant when you said you're 0, 1, not plus minus 1, no, right?
Yes. So really, the fact that the correlation. Okay, so I see your point. So really, if we want to go from the indicator to the end function, we need to multiply it by 2 minus 1. So this means that either the constant function correlates with t, so either t is slightly biased, or the end function correlates with t.
I guess my confusion is again about correlation. I mean, usually when you started, you talked about correlation between plus minus 1 functions.
Yeah.
But here you're talking about different kind of correlation. So the function is allowed to say, I don't know, that's 0, right?
No, so I'm converting this indicator. I'm converting it to a real Boolean function, to the end function. And this end function correlates with t. Notice that even though the end function gets 1 with a low probability, it can correlate with a balanced function. So let's say that every time that the end outputs 1, then I get the value correct. So this gives me that with probability epsilon, I get the value correct. And every time the end is 0, I get the value correct with probability half. So this gives me epsilon plus half minus epsilon over 2. So this gives me half plus epsilon over 2.
Okay.
So a very biased function can correlate with a balanced function. The correlation will be small.
Thanks.
Okay, so now we reach the third part of this talk, and I will describe two applications. The first application is improving Andreev's lower bound. Recall that the best known lower bound was for the Andreev function, and this was n cubed over log squared n. And now I am ignoring log factors. And this lower bound is nearly tight because for the Andreev function we have the upper bound n cubed over log squared n. And we will see this function in the next slides. The first application of our hardness reduction will be to show that the function suggested by Ilan Komogoritsky and Ran Raz, which is a variant of the Andreev function, actually has formula size bigger than the Andreev function. It has formula size n cubed over log. This improves by logarithmic factors both the upper bound and the lower bound for the Andreev function. So it is provably harder than Andreev's. And I want to describe you the construction both of the Andreev function and the Komogoritsky-Raz function and the analysis of the two of them. So in order to do that, I want to describe first what is the composition of Boolean function. So take two functions, f and g. Both of them takes many inputs and output one bit. How can you compose them? So the way to do it is you take many copies of g, and you take each copy on a different set of variables. So if f has n inputs and g has m inputs, the composition has n times m inputs. A natural question to ask is what is the formula size of a composition of two functions? This was asked by Karchmer, Raz, and Victorson. And a straightforward argument shows that the formula size of the composition is at most the product of the two. Why is that? Because we can take a formula for f and replace each leaf with a formula to g. This would result in the number of leaves, which is a product of the two sizes. And KRW suggested that this is nearly tight. They conjectured that the composition really behaves like the multiplication of these two sizes. And a positive answer to their conjecture would show that a candidate that they suggest requires formula size super polynomial, n to the log n. This would be huge. This would separate P from NC1 because their candidate is a function in P that under the conjecture require super polynomial formula size. So this is really a big question. It remains open from the early 90s. Yes?
Sorry, and you need to show this for a specific f and a specific g, or it's a whole family of them? Or?
So the conjecture is that it works for any f and g, but actually to get the result on KRW, it is enough to look at, let's say, the worst, like an arbitrary f and a random g. So it is, and it's also enough to prove slightly low, weaker results than that in order to get the n to the log n. But actually, so it makes sense to ask it even for any two function f and g. So there is one counterexample, but this counterexample just you gain a factor of log. So there is some function where you get that composition is the product up to some log factors, but I don't know of any examples that is more significant than that. Okay, so this is really a big open question, and I want to mention that even understanding special cases of this question may lead to important lower bounds. The first special case, which is known to be true, is when g equals parity. So when f is any function and g equals parity, this is true. The composition really behaves as the size of the composition is the product of the sizes, up to a constant. This is enough to show the lower bound for the Andreev function. So only this special case is enough to show the n cubed lower bound. It is still open what happens if f, the top formula, is a parity function. This was suggested as an open question, as a special case by Gavinsky, Meir, Weinstein, and Victorson. And this would give you another construction with lower bound n cubed, which is different than the Andreev function. one more special case that I want to mention is what happens where both f and g are randomly chosen functions. In this case, it seems that they don't have any structures that you can exploit in the composition, and really the best way that you can do is simply do the straightforward argument. However, we still don't know this special case, and if you can prove this special case, you can convert it into an explicit construction without any randomness that requires formula size n to the 4. So I wanted to mention this very beautiful open question, but actually what I'm going to use from this slide is just the definition of composition and this special case where G equals parity. So what I'm going to use? I'm going to use the fact that when you compose with parity, the formula size is the formula size of F times the formula size of parity, which is up to a constant m squared. And now I want to describe Andreev's construction and the lower bound for Andreev. So Andreev first uses the fact that there exists a function on log n bits with formula size omega n. And this is simply by a counting argument. You count how many formulas you have of size roughly n, and this is smaller than the number of functions on log n bits. So it must mean that there exists some functions that cannot be described by one of these formulas. In fact, most functions will not be described by a small formula. And you have here really an exponential dependency between the number of variables and this formula size. In other words, you can say that a random function will have this property. And Andreev's idea is to convert this randomness to be part of the input. So Andreev, instead of thinking of the input as one string, you think of it as two strings, x and y. You should think of x as the randomness. Both these strings will be strings of length n. And the first thing that you do is you do a mental experiment and you think of x as a truth table of a function on log n bits. Then you compose f with the parity over n over log n bits. This gives you a function on n bits. And you evaluate this function on y. So this is Andreev's function. And let's see the lower bound for this function. So if you want to compute this function using a formula, formula size is at least the formula size when you fix the first input x to be the truth table of this function f0. So you think of it as fixing the randomness to be as the truth table of the function f0 on log n bits. So to describe a function on log n bits, you need a truth table of length n. So this is why the parameter works out. But now when you fix the first input, x, to be this truth table of f0, really the function is the same as the composition of f0 and parity. Okay, the only input now is y, and as a function of y, this is f0 composed with parity. Now we are using this theorem from above, and we get that the size for this function is at least omega n times the size for parity, which is n squared over log squared. Overall, we get n cubed over log squared. Okay, so this is Andreev's construction and the analysis. Now we get to the function of Komogolsky and Raz. So, okay, so I just wrote the Andreev function here because it will be very similar to KR construction. So we take the function described by x composed with parity. Ilan and Ran add an additional step. So you start again with x and y of n bits each, and you take x and you encode it using an error correcting code with very good relative distance and length, which is polynomial in n. Okay, so first you do this. So you replace the string of length n with a string of length polynomial in n, as the distance between any two such strings is roughly half. It's very close to half. Now you view this longer string, this string of length poly n, you view it as a truth table of a function on order log n bits. And now you do the same. You compose the function with the parity and evaluate it on y. So overall, if you want to write it succinctly, you take the function described by this encoding of x, compose it with parity, and evaluate it over y. So this is what we have, and the error-correcting code is very good relative distance. And now we can use Johnson bound to show that most code words are far from all truth tables of small formulas. So previously we used the counting argument to say that most truth tables are not described by small formulas. But now we want to show that they are even far from all formulas. So the way we do it, we take a ball around each small formula. This ball does not contain too many code words. This is using the Johnson bound. And then we take a union bound over all possible balls, and we don't cover, we cover a small fraction of the code words. So this shows that most of the code words do not appear in any of these balls, so they are distanced from all the small formulas. In other words, what does it mean? It means that the function described by this code word, or most such code word, is omega n hard for agreement half plus 1 over n. Yes.
Okay, one small question. Now, the formulas you have in mind now are formulas over like poly n inputs, right?
No, so I think of them as formulas over so I think of this function f(ECCx). This is a function on order log n inputs, actually.
Right, but I guess what I'm saying, this order log n is now a bigger constant times log n. So
right.
Potentially a random function there would require poly n
right.
formula size. But you're just saying it's at least omega n. You don't want to.
Right. So I cannot, since I'm using counting arguments, I cannot use the fact that these look like a total random function on order log n variables. I'm just using the fact that for linear size formulas, they are average case hard.
Okay, because the number of code words is only n and not poly n.
Right. It's 2. Yeah, the number of code words is like 2 to the n. Yeah, that's a good point. So we could hope maybe that this function is even harder than that. So it is possible that this function is maybe n squared hard or something like that. Okay, but this is what we can prove using Johnson bound and just counting arguments. And now we get, using our reductions, it's this function on log n bits requires formula size n times log n. And now we use again the composition to show that the KR function requires n times log n times n squared over log squared. In other words, we improved by a factor of log n. So this really finishes the first application, where we've shown that you can get a factor of log n because we didn't pay much to get this average case hardness, right? So we didn't pay with the parameter much. We just took the parity. Instead of n over log n, we took it to be of size n over order log n. But we gained in the average case hardness, which gives us more in the worst case hardness. It gives us an additional factor of log n. Okay, in the next, this shows that you can gain some logarithmic factor, but you would hope to get maybe a factor of n, because the hardness could be exponentially close to half the average case hardness. In the next slide, we will do it, but this would be for a randomized construction. Okay, so we begin with a question. Now forget about the plus minus 1 notation, just do 0, 1 notation, work over GF2. And I ask, what is the formula complexity of a random degree D polynomial? So for example, a degree 2 polynomial is simply this sum over i's, sum over j's, Aij is xi times xj modulo 2. And think of this Aij as picked uniformly at random. So again, since we have n to the d parameters here, we will need, most degree d polynomials will require size n to the d. This is a simple counting argument. However, if we want to compute this degree d polynomial by a formula, the simple suggestion is just to take the sum of all these monomials modulo 2. The problem is that with the Morgan formulas, we cannot compute the sum modulo 2 efficiently. We need size quadratic in the number of terms. So we have n to the d terms. So the size would be n to the d squared, or n to the 2d. So the upper bound is n to the 2d, the lower bound is n to the d. We suspect that the upper bound is tight. So the conjecture is that the upper bound is tight. If this conjecture is true, then using the ideas of Andreev and converting the randomness to be part of the input, along with composition with parity, you can construct an explicit function whose formula size is almost n to the 4. So there's a bug in the slide. It's n to the 4 minus epsilon, actually. So you can get close to n to the 4 if this conjecture is true. Unfortunately, I'm not sure that this conjecture is true. I cannot prove it yet. What I can show you is a non-trivial lower bound. So using our reduction, we can show that most degree d polynomials require size n to the d plus 1. And this really gives us a factor of n improvement over what we could do without our reduction. And how do we do it? We are using, again, results from error-correcting codes, namely the result of Tali Kaufman, Shachar Lovet, and Eli Porat. And using this result, we show that most degree d polynomials are not only worst-case hard with size n to the d, but they are average-case hard with parameter n to the d, with agreement exponentially close to half. Okay, so this is really the smallest agreement that you could hope for, because these are functions on n bits. And then you convert this Harvard-case hardness result into a worst case using a reduction, and you get that most degree d polynomials require size n to the d times n. So really here, we got a factor of n improvement over the trivial counting argument. And this finishes the second application, and actually it finishes the talk. So I would like to thank you very much for listening, and I will be happy to answer any questions that you would have.
Okay, thank you, Avishay. Any questions? Anyone?
Can you go back to just the last slide?
Yes. Yeah.
Can you say why they, so how does the result show up in error correction?
Yes, yeah. I should have said more about this, sorry. So really the result talks about the Reed-Muller code, and they show a least decoding bounds for that. So really when you talk about degree d polynomials, this is the truth table is Reed-Muller code words. And they show that if you take a ball around any point, then it doesn't contain a ball with radius half plus 2 to the minus omega n radius, then it doesn't contain too many code words. It doesn't contain too many degree d polynomials. It contains a lot, but 2 to the little o of n to the d. And this is enough to afford for a counting argument and go over all possible balls around small formulas.
Thanks.
Yeah. So really, we're using the fact that we have some least decoding bounds in these codes. This was used in both applications, actually.
So another sort of vague high-level question, but your results, so it feels like pretty big detour, right? I mean, you go through different steps of approximation by different kinds of objects until at the end you get approximation by
That's true.
Single and, right, for the top part of your tree. You go to polynomial, then you say polynomial gives you parity, and then parity gives you hand. Well, I guess you thought about trying to take shortcuts, and then you said that you don't know how to do it, but it's yeah. Sorry, this is not a question. I was just
Avishay, are you still with us? So I think, yeah,
oh,
the question was too difficult.
I asked the wrong question.
You shouldn't ask such questions. So because apparently we lost Avishay, so the timing is perfect, I think. Let's stop here, but people are welcome to stay around in case Avishay comes back. And again, in 2 weeks, we'll have Mohsen Ghaffari. So let's end here. Thanks everyone for joining, and hope to see you in 2 weeks. Thanks again to Avishay for the great talk.
Okay, so I'll take us offline.
Yeah,
but I'm sure Avishay will show up in just a minute, so you guys can stay with us.